I'm going to show you what a vector space is. I'm going to illustrate to you what a vector space is and what is not. So a vector space is a collection of elements, of numbers, of, that satisfy these 10 properties. One of those properties is, it's also, we can also define the operation. Normally, the operation that we define is just addition and multiplication as it is, but sometimes it's defined differently. And we want to know if we define an operation in a certain way, will that satisfy these 10 properties? Okay, so let me show you, like, for example, number 1. It says it's closed under addition. Let me show you what that means. Let me move this to the side. So imagine the set of even numbers. Let's call it A. And we have the set of even numbers 0, 2, 4, 6, etc. Those numbers. To be close under addition means that if I take two elements of the set A of even numbers, I'm going to end up in the same set again. Like if I take 4 and 6, what do I get? I get 10. And if I take, say, 20 and 30, I get 50. Meaning, if I take elements from here and I add them up together, I'm always going to end up with another element from that set. And I will have to prove this generally, not just give precise examples. But for the sake of time, I just wanted to illustrate to you what that is. Now we can have another set, say the set of of odd numbers. Let's say like 1, 3, 5, 7, odd numbers, etc. Forget my bracket there. The point is that even numbers are close under addition because you can take two numbers from this set and add them up and you get another number that is also in the set. Whereas over here in the set of even numbers, if you take two elements from there, you're not necessarily going to end up in the same set. Meaning, take the 1 and 3. They're members of the set B. So 1 and 3, I add them up, I get 4. I got an even number, and that number 4 is not in there. It's in here. But the point is that 4 is not there. Therefore, B is not close under addition because I found a counterexample. Whereas over here, like I said, I will have to prove this generally. It's close under addition because no matter what two members I get, I always end up in the same set. Now let's do another example that relates more to linear algebra. Let's do the set. Here's the set of all ordered pairs x and y such that x and y are greater than or equals to 0 and they're also less than or equals to 0. Never mind the notation. Like if it's not proper or you kind of don't understand what this means. All this is saying is if you have a graph, right, where this is the y-axis and this is the x-axis. Make sure this is recording. It is. Okay. We care about this region right here. This is where x and y are positive, this region. And we also care about this region. This is the region where x and y are negative. And that's all what the set is doing, the set R of the region. So the question is this close under addition? Meaning, if I take two members from this set, will I end up in the set again? Well, I can take this dot right here, somewhere in here. Let's say that's 2, 2, right? 2, 2 is there. I can also take a member from this region, this area right here. Let's say somewhere over here, we have -1, -3. Okay. If I add them up together, will I end up somewhere in the region, in the shaded region? Well, let's see. I have 2, 2 plus this vector or this element minus 1, minus 3. What do I get when I add them up? Well, adding corresponding terms, you know, I get, what do I get? I get 1, minus 1. And you can see the 1 minus 1 is not in the shaded region. In fact, 1 minus 1, it's somewhere over here at the bottom. See, 1 to the x minus 1 to the y, somewhere over here, meaning this 1, minus 1 is not in the set R, on the region, whatever. That means the R is not close under addition. Now, there's something that I'm kind of not really talking about because I don't think it's important yet, and that is the operation. You know, I'm assuming, like right here, the addition works as adding corresponding terms. You know, like you add 2 with this 1 right here, and you add this 2 with this 3 right here, meaning you add corresponding terms. But it is not always the case that you can do that. But for now, because I want to illustrate what close under addition means, you know, I'm just, you know, assuming that this is how addition works. So anyways, so I just show you, I give you some examples of what it means to be close under addition or not close under addition. Now, check this other example. You can have that set R, let's call it R1, of all order pairs x and y, x and y, such that x, y are positive. And the question is this also close under addition? Well, you can do another graph just to illustrate, you know, what that means. This is the y-axis, this is the x-axis. We're talking about this region right here. Talking about that region. So if you take members from that region, are you going to end up in the same region? You know, it looks like you will, but we're gonna address that right now. We're gonna move up to the next step, right here. It says that a vector space has to be closed under multiplication. You see number 2? Has to be closed under multiplication. If you deal with normal, real vector spaces that you probably have been dealing all your life, then yes, that's true. That's like common sense. But I'm going to show you that sometimes that's not true. Like here. See, we're on number 2 right here. So why is that? Because if you take an element from this set, let's say 1, 1. You know that 1, 1 is a member of this set, and it's in fact somewhere over here, let's say, right there, somewhere over there. But it's a close under multiplication. Well, that means that if I multiply by a scalar r, and I choose the scalar to be -1, I'm gonna get -1 times 1, 1. And that tells me that applying the normal multiplication of scalar multiplication of vector spaces of vectors, I get this -1, -1. And you can see that that point is not in the shaded region up here. Excuse me. That is somewhere over here. That point is somewhere over here. In other words, as far as it is concerned, the set R1 is not close under multiplication. I'll just show you right here that it's not close. Because R can be any real number, and I choose R to be -1. And when I do that, it's gonna give me a number not in the region, and so it's not close under scalar multiplication. Okay. So let's move to the third step, which is addition is commutative. You know, that kind of seems to be common sense. Number three, addition is commutative. Is as if I say, let me write down number three. Is if you take two elements from a set, say X and Y, they're members of a set S, whatever, you know, if I have this X plus Y, question, will that be also equals to Y plus X? You see, it kind of seems like common sense that it is, but that's only because if you've never seen vector spaces, your mind is like, oh, you know, you're used to dealing with just regular real vector spaces. But sometimes this is not true. Let's see. Let's define the operation in this case. We can talk about the operational differences. You know, if you talk about differences, you know that X minus Y is not the same as Y minus X, right? But, you know, let's define addition as follows, meaning as a difference. Let's have a set D for difference, be the set of all order pairs X and Y, such that if you had two members, let's say X sub 1, Y sub 1 added to X sub 2, Y sub 2, you are going to get X sub 1 minus X sub 2, comma, Y sub 1 minus Y sub 2. So all I'm doing is just defining how the operation of addition works in this set D. And the question is D commutative? Okay. Okay. So let's try out. Let's try out the addition x1, comma x y1 added with x sub 2, y sub 2. By definition, I get this difference. I get this. I already explained that. Okay. But now, if you turn around, if you have x sub 2, comma y sub 2 added to x sub 1, y sub 1, now you're going to get the difference of x sub 2 and x sub 1, comma y sub 2 minus y sub 1. Anyways, the point is that if you flip these guys, you are going to end up with this. And you know that these two are not equals because corresponding terms are not equals. In order for these two vectors to be equals, corresponding terms, meaning this first term, must be equals to this first term, and this second term must be equals to this second term of the order pair. And because they're not, you see here's the difference of y sub 1 and y sub 2, and right here is the opposite, y sub 1 and y sub 1. Anyways, they're not equals. So that means that the set D, as far as we're concerned, is not commutative. And that's just an example of how there's something that looks obvious is false for certain sets, for certain operations, like the operational difference or the set D. Anyways, let's keep moving here. What do we have? We already covered 3. 4, addition is associative. You know what that means? Addition is associative. We're going to need 3 vectors for this. Let me just draw a line right there. What that means, we can use the same set D, okay? The way it was defined. We can take 3 elements of D. For example, we can say inside brackets x sub 1, comma x sub 2, plus y sub 1, comma y sub 2, plus the third vector. Now, when I say vector, I don't mean vector space. I just mean a member of the set D. But anyways, because we don't know yet if it's a vector space. Will this be equals to this? Question again, will it be equals to x sub 1, comma x sub 2 plus brackets y1, comma y2 plus c1, comma c2. like I said, it looks obvious if you're not used to dealing with what I'm showing you, operations that, like the difference, So let's do this addition following this definition. I'm gonna get the difference like this. Right? When I do the operation inside the brackets, I get this, following this definition. And the guy outside just is the same. I haven't done anything to the guy outside. It just is the same. But when I add them up again, I need to follow the same definition of D, which means I'm gonna get this. Right? So by definition, I get this. Now my question is, would this be equals to this if I now instead add these two guys together? Well, the guy outside is still the same because I'm gonna perform the addition inside the brackets first. So I'm gonna get inside the brackets by following the definition of what D means is the difference of Y1 minus Z1, comma, Y2, Z2. That's by the definition of D. Now I can add these two guys. I can get rid of the brackets and I can add these two guys. And when I do that, again, I get the difference. So I get X sub 1 minus Y sub 1 plus Z sub 1. So I have to change the sign of the Z because I'm doing the difference of Y and Z. I get here X sub 2 minus Y sub 2 plus Z of 2. And again, this addition, this operation, by definition turns into this from the definition of what it means to be a member of D, of the operation defined in D. And you can see that they're not equals. This guy is not equals to this guy because you have here a positive Z1 and right here you have a negative Z1. In other words, something that look obvious, they're not equals, it fails. So addition is not associative for the set D. That's an example of how addition is not associative. Okay, let's move to the next. Let me move this to the side. So we cover 4. Addition is associative. Well, we know that sometimes it's not. 5, multiplication is associative. Well, more than anything, multiplication being associative just follows from the definition of the real numbers, scalar real numbers. Let me see. So what that means is that if you have two real numbers, say R1 and R2, those are real numbers, and you have a vector, let's say the vector is the order pair X, comma Y. And the question is, if I do R1 multiply with the multiplication of R2 and the vector, will that be the same as if I first multiplied the real numbers or the scalar numbers and then I multiply it with the vector? Well, yes. That's, by the way, this is a definition. We don't have to prove anything. I'm just illustrating to you that this is actually true because we're using the the R1 and the R2 are real numbers. So we're using the property of real numbers that says that real numbers are associative. So yeah, it's true. So this is just, it's just true. At the moment, I couldn't find an example where this would fail. But I just thought of one, actually. I can define multiplication, but let's just leave it for that right now. Let's move to number 6. I'm just illustrating what a vector space is. So looking at number 6 right here, as I said, this is a checklist. There's nothing to prove here. These are just definitions of what a vector space is. A vector space is all these 10 definitions, and I'm just illustrating what they are. So number 6 is saying the existence of an additive identity, 0. Existence of an additive identity. Okay, so what that means is that if you have a vector, say x comma y, and you add another vector to it, you are going to get the same vector. That's why it's an identity. Because whatever vector you start out with and you add it to another one, you ended up with the same vector. Nothing happened to that vector. And so we can think of that vector, we are so used to the 0, that is 0. See, that vector added to the 0 vector is just a number. So that's why this number is additive identity. Let me see if this is recording. Okay. Now, you also have to check this property that you have to flip them around and you have to test this too. And you would think you have to test this. Now, the reason why you cannot skip the second equality is because at the moment we don't know if this is a vector space. Because if we knew that it's a vector space, then we can skip this second equation, because if the first one is true, if this first one is true, then we know that because it's a vector space, it's commutative. Addition is commutative, and so this would also hold true. But because we don't know if it's a vector space yet, we also have to check the second property too, okay? Just remember you have to check that. Let's see. Let me define this operation as x plus y is equals to x times y. Here I'm treating these real numbers, x and y, as if they're vectors. You know, real numbers can also be treated as vectors. And I'm defining, meaning I'm choosing just because, the addition of those two numbers, or those two vectors, to be a multiplication of the real numbers. And I'm defining the scalar multiplication to be x to the r. I can also define additional things like the vectors have to be positive and x cannot be 0. But just, you know, for the purpose of this illustration, I just want to show you that I can define the addition as this multiplication. Okay, bear with me here. I know it might be different than what you're used to, but see, in this case, if you take 1, let's say, if you take x plus 1, by definition of addition, you are going to get the multiplication of x times 1. And x times 1, because they're real numbers, you're just going to get x. And also, if you do it the other way around, meaning commutative, 1 plus x, you get 1 times x, which is just x again. See, in this case, the 1 is behaving like the 0, right? Because if you have x plus the element, it's as if, you know, normally it's as if if nothing happened to the x, you just get the x. So it's like behaving like a 0, but it's not a 0, right? And that's why we don't call 0 just 0. We call it the additive identity. If you forget the names, don't worry about it. The purpose of this example is to show you that the additive identity is not necessarily 0, 0, 0. It sometimes looks different, like a 1 in this case. And that was just the purpose of showing you this. In fact, just before I leave this example, if you have, check it out, if you have x plus 0, you are going to get x times 0, which is just 0. So in a way, 0 is behaving as if it's a minus x. So it's like x minus x, you get 0, you know, and also the other way around, you get the same thing. by the definition. Just to show you, sometimes vectors or operations behave in a way not expected. Okay. Let's go to number 7. Right here, number 7 is existence of a multiplicative identity 1. Okay. What that means, let me move this to the side. I'm doing a lot here. That would mean like if you had the scalar 1 and you multiply it by a vector, like say x comma y, you get the same. Nothing happens to that vector. That's why it's called the multiplicative identity. 1 is the multiplicative identity. And as an example I did earlier, if you try, in this example right here, looking at this example, if you let r equals 1, you can get r times x. By definition is x to the 1, right? Which is just x. And I'm showing you how it behaves. It behaves not the way you were used to it, but it behaves this way. And in fact, if you're dealing with matrices, this is the multiplicative identity of a 2 by 2 matrix, So it doesn't necessarily look like a 1. It looks a little bit different. The reason why is because the operation defines it. So because if you multiply this matrix than this random matrix, let's say, if you follow the operations on matrix multiplication, you are just going to end up with the same matrix, A, B, C, D. And so I'm just showing you that it doesn't just look like, because I got to tell you, when I first saw this, I thought that the multiplicative identity would look something like this, and I was wrong. And it looks like this. And the reason why it looks like this is because there's a way that the operation of multiplication is defined. And so you got to follow the definition so that when you multiply and you end up with the same number, these two are the same. That way you can say that this is the multiplicative identity. In other words, it behaves like a 1. So this is not the multiplicative identity. It's this one right here. So it looks different, right, than what you would expect. Okay, so let me move this to the side. So within number 7, existence of multiplicative identity. Now let's go to number 8, multiplication, distributed over addition. Okay, what does that mean? Well, what that means, just an example. If you have a scalar r, meaning a real number r, and you open brackets here, you multiply it by the addition of 2 vectors, so 2 elements, x1, y1, plus x2, y2. See, we are expecting to get this. It might not be the case that we get it, but we are expecting that we're going to get this. What's the other one? R. Right? That is expected. Also, if you're dealing with matrices, just for the simplicity, for illustration purposes, let me show you. Let's say A, B, C, D, plus a different 2 by 2. It doesn't matter how they look like. They're just elements of a set. This is how the elements look like. This is how the elements look like. It doesn't matter. All I want is that if I'm going to add them up, I'm supposed to distribute the scalar over the addition as follows. That's all that matters, you know. And the question is, well, is that true? Like I said, and check it out. Check this out, you know. And the other example that we had earlier, let me just write it down here as a little recap, where I had x plus y equals xy, and I had a scalar r times x equals xr. You know, remember that from earlier? Here, you can see that r multiplied by the addition of x and y, which are real numbers. I mean, they're vectors, but they're also real numbers. You're gonna get by definition r times the multiplication of x and y, right? The addition turns into multiplication by this definition. And by the same definition, when you multiply on a scalar with x, it turns into an exponent. So this will be equals to xy to the r, which again, by definition, of real numbers is nothing more than x to the r, y to the r, which is just, again, by definition, you can go back to when you have two numbers multiplied together, you can break it down into an addition. So you have two numbers multiplied together, you can break it down into an addition as x to the r plus y to the r. And one more time, you can, when you have exponents like this, again, you can go back, like here you have exponents, you can go back to the scalar multiplication. So this is just equals to rx plus ry. In other words, r, x plus y is indeed distributed as rx plus ry. But not because the way you would think. You have to go through the definition, like I just did, to prove that indeed it holds true. Because sometimes it doesn't. I'm going to give you an example that it doesn't. Let me just make sure this is recording. A little while ago it wasn't recording. I'm going to define an operation, you know, as follows. X comma y, that's just normal addition. I'm defining it, by the way. I can define it as whatever I want. The problem is it a vector, you know, is it a vector space, you know? So I'm going to define this as the addition of corresponding terms. Like that. Not brainer right there. It's just, you know, I'm defining the addition as the addition of corresponding terms. But the scalar is where it's going to change your perspective. So I'm going to define the scalar to be x comma 1. In other words, it seems like the only effect r had an x, it was just nothing, you know, but the y turned into a 1. And this is just the definition. I'm defining it that way. Now, will this property of scalar multiplication over addition distribute over the addition? Will it hold true? Well, let's see. I have the scale following this, okay? Pay attention here. Don't pay attention over there. Pay attention here now. I have the scalar r, brackets, the addition of two elements, x comma y, x sub prime, y sub prime. You are going to get, by definition, you add them up together. What's inside the brackets? The r outside stays the same. You get x plus x prime, y plus y prime, like that, right? I took care of what's inside the brackets first. And now I'm going to apply the definition again of scalar multiplication. And it says that the first term stays the same. So the first term stays the same, x plus x prime. But it's saying that the second term turns into 1. Okay, the second term turns into 1. So that is the definition of the scalar multiplication. Fine. Now, let's try this. See, I'm hoping that this is equals to this, but I'm going to show you that is not the case. So right here, again, following this definition, you get the first term stays the same, but the second one turns into 1. Likewise, this first term right here, the first term x prime stays the same, x prime, and the y prime turns into 1. There it is. And now when I add them up, I had to follow the definition again, but it's saying that in definition we add corresponding terms, so we get x plus x prime, comma, corresponding terms of adding 1 and 1 is 2. And you can see that they're not equals. In other words, yeah, these two are not equals. So this was number 8, right? Multiplication fails to be distributed over addition. So this is not a vector space. Okay, let's move to the next one. What would the next one be? Right here, number 9. Addition is distributed over multiplication. In a vector space, addition is distributed over multiplication. You know, let's see an example where it doesn't, or it does do that. What that would mean is this, guys. If you have two scalars, R1 and R2, those are scalars, those are real numbers, those are not vectors. And you multiply with the vector, say x comma y, you're supposed to get this. X comma y plus r comma, like that. You know, it kind of makes sense. You're supposed to get that. Well, that kind of makes sense if you're dealing with real vector spaces, you know. But sometimes you're dealing with stuff that the operations change. So let's see. I'm going to define another operation again. When you add two vectors, let's say these two vectors, you are going to end up with the addition of corresponding terms. That's easy. That's usual. But I'm going to change scalar multiplication. The scalar multiplication of the vector is going to be Rx comma 1. That is the scalar multiplication, defined. Okay, I define it. Just because I can define anything I want. It's definition. I'm defining this set. Would this be a vector space? Let's see, we're on 9 right now. So let's try it out. So you have R1 plus R2. See, I'm trying to do this right here. Multiplied by the vector x comma y, I get R1 plus R2 times 6 plus 1 changes. Okay, let me explain to you what I just did. Sometimes even I get confused because of the operations. So when you multiply this, these are scalars and this is a vector. You follow this definition right here. And it says that you're going to multiply r times the first term. There it is, r times the first term. Okay, likewise right here, you multiply the scalar times the first term. And this is the scalar times the first term. And then you do the comma. And then when you multiply r times y, you're supposed to get 1. So this y turns into a 1. And there it is. This multiplication turned into this. Simple, huh? So now let's see. That's it. You know, I want to see if this holds true. R1 multiplied by the vector x comma y, and then add it to the second vector like this. Let me show you what I mean right now. So I want to know, see, if you were to distribute this addition over this vector multiplication, you will end up with this. So I want to see if this is equals to this. I want to see if the two are equals. So here, following the definition that is up here, this definition, the definition says that I'm going to get this. I'm gonna get R1 x comma 1. So see, when you multiply the scalar times the first term, that's what you get. The multiplication of the scalar times the first term. But the second term turns into 1, and there is a second term. And likewise for this. So I'm gonna get R2x comma 1, following this definition up here. And then now to add them up, I'm gonna follow the definition of addition, which is this definition up here, add corresponding terms. So if I do add corresponding terms, I'm going to end up with this right here. R1x plus R2x, that's in the first term, comma, add the second term, and the second term you get 2. You get that. In fact, let me just factor it out right now really quick. You get this, R1 plus R2 times x, comma 2. What this is showing you is that this guy right here is not equals to this guy. They're not equals, meaning this are not equals, meaning addition of a scalar of scalars is not distributed over multiplication of a vector. See, the addition is not distributed over the vector. Like, because if it were, then it will be equals to this, but it's not. So that was just an example to show you how it fails. Okay, let's move to the last one. The last one is the 9. Okay. Existence of additive inverse. Minus x for every x. So what that means is meaning whatever number you give me, or whatever number is part of the set, or whatever number is part of the collection, we can find another number that when you add them together, you get the additive inverse. You get 0, let's say, for real numbers. So let me give you a quick example of what that means. So, see, let's say if you have 1, then the additive inverse of 1, from the real numbers, is minus 1. Because if you add these two guys together, you get 0. And it just kind of makes sense that for this number 2, the additive inverse is minus 2, because if you add them together, you get 0. And likewise for 3 is minus 3, etc. For x is minus 6. And now check it out too. Each number, like here 1 or 2 or 3 or x, has its own additive inverse, meaning the additive inverses are different for each number. It's like 1, minus 1 meaning, is different than minus 3, obviously, right? So each number has its own additive inverse. And like I said, this is just a definition. We're not trying to prove anything. So in real numbers, you would have, if you have this order, this vector, x1, x2, and you add it to another one, so that you get 0. And the question is, what number or what element is this? And whatever number it is, we can define it as minus x1, x2. We know that for real vector spaces would be this. Negative. Right? But now, remember the definition that we had earlier where x plus y was equals to xy, and the scalar xr times x was equals to, like this, the exponent? See, like in this case, if you add x and 0, you're going to get x plus 0. You're going to get x times 0, which is just 0. So in other words, 0 is the additive inverse of not just a particular element by every single element in this definition. See, like in here, the additive inverse is different, right? For each element is different, but here the additive inverse is the same for every element. And also, if you have the set, just this is another example, but talking about additive inverses also, consider the set of bits, just the set 0 and 1. It has two elements only, 0 and 1. There's no -1, there's only 0 and 1. See, in this case, if you add 1 to itself, like 1 plus 1, you get 0. In other words, 1 is the additive inverse of 1, because you get 0. You would expect the -1 is the additive inverse of 1, right? Because normally 1 minus 1 is 0, but in this case, we only have two elements, 0 and 1. There's no -1. And it works out that the 1 is the additive inverse of 1. And also 0 is the additive inverse of 0, if you think about it, because 0 plus 0 is just 0. So 0, does have an additive inverse, and it's 0. Of course, 0 is also its additive identity, but that's besides the point. Just wanted to illustrate to you the 10 steps, the 10 definitions, and I just did that. So a little recap. A vector space is a collection of elements that satisfies these 10 properties. And sometimes, if you study this by yourself, you can see that maybe you have fewer definitions. Maybe you have 8 definitions, but the reason why is because they combine some definitions, you know. But generally speaking, there are 10 definitions, and these are the 10 definitions. So if all of them check out, you know, if you have a collection of elements and you run through each of these definitions and they all hold true, then you have a vector space, and there's no shortcut. You have to go through each of them to verify if a collection of elements is a vector space. Okay. If it fails a single one of these definitions, then you don't have a vector space. And the reason why I chose to approach the definition of a vector space as I just did is because there are a lot of videos out there that show you what they are, but they don't really show you what they are not. And that's why I chose to go this route. And as I make more videos about the subject, I'm gonna be specific about vector spaces when it comes to real vector spaces, complex vector spaces, and vector spaces over matrices. Okay, so that's it.